Hello everyone, my name is Aaron Stannard. I'm the founder and CEO here at Petabridge, and today we're going to be making good on a promise I made on Twitter, which is we're going to make a YouTube video about profiling .NET applications with PerfView. Now, even if you've been in the .NET space for a long time, you may have never heard of PerfView before, and that's pretty normal. It's a relatively obscure tool that was developed by Microsoft 10 plus years ago to analyze event tracing for Windows data. But the reason why it's significant is that PerfView is the tool of choice used by the core CLR team, the ASP.NET team, and so forth to profile the performance of .NET applications. Now, I've given this talk before where I've discussed the difference between profiling and benchmarking. Tools like benchmark.net are great for benchmarking, but sometimes when you're trying to diagnose a performance problem in a real-world application, you actually need to use a profiler to go and do that. And there's a number of different tools out there that are available and will help you do it. PerfView is free, it's open source, and it uses really low-level events that are emitted by the .NET runtime to help you kind of work backwards from what the CLR was doing, why it did what it did, and also how maybe different parts of the .NET system may have interacted with each other, such as the garbage collection system and the threading runtime, for instance. Now, one constraint that PerfView does have is that it is Windows only. It depends on event tracing for Windows, which is a operating specific construct. It's a high performance tracing system that's used by Windows applications, and thus the core CLR uses it as well. So you're probably not going to be able to use PerfView to collect data on a platform like OS X or Linux. That's okay. The other constraint that's worth bearing in mind is that in order to get usable information for PerfView, you're going to need to be able to run it on administrator mode. So we'll demonstrate that when we actually do some PerfView data collection later. But for the time being, that's something that's worth bearing in mind. Now, PerfView does both data collection and visualization. It'll give you flame graphs, kind of showing you where all the hot call sites are. If you do CPU profiling, it'll help give you some tables that'll understand the way garbage collection performed in .NET. And this is really helpful. If you just need to analyze PerfView data that somebody else collected, you do not need to be in administrator mode to do that. Now, one of the reasons why PerfView is so popular is that the data format that it exports is very easily shareable between users. So for instance, I just spent some time over the past couple of weeks investigating a .NET 6 performance regression in Akka.NET, which is the library that our company Petabridge maintains. And I was able to collect data on my machine and share it with members of the core CLR team who were able to analyze it really easily. Most profiling systems don't port very well. It's kind of difficult to export data that someone gathered on one machine and analyzing it on another. PerfView does not have that problem. It's very easy to go and export data back and forth. What data does PerfView collect? Well, PerfView collects runtime events, such as events emitted by the .NET runtime. This includes garbage collection runs, changes to the thread pool, contention between threads. It also can include events from the just-in-time compiler, and also things like symbol loading. Like if you dynamically load a DLL at some point in your program's execution, you can actually see what's happening based on the event tracing for Windows data that's being gathered. It also gathers runtime events from Windows itself, so you can even keep track of things that are somewhat esoteric, such as the amount of electricity your computer is using at a certain point in the benchmark. And you can also measure custom event tracing for Windows events as well. The system.diagnostics.trace library will give you some tooling to help do that. It also will collect some system data, such as the total amount of CPU and memory usage. It can do this on a per core basis as well, which is quite useful. And you also will get some application data. So for instance, when you're running PerfView, it has the ability to get call site information from your .NET applications, which will help show you, okay, these are the most frequently called methods at this point in your application, and it can give you caller-callee information, data about the hot paths that are occurring there, and it can also kind of trace and correlate this application trace data to the other events and system data that's being gathered as well. So it gives you a fairly rich view of what's happening on your machine while it runs. Now, the first question you might be asking is, okay, so how do I actually go about installing PerfView? PerfView does not have a tremendous presence online in terms of its documentation and everything else, but the easiest way to install it is via Chocolatey. So you can just go ahead and copy this command in here, choco install PerfView, and that'll make PerfView available both on the command line, which is what we're going to use for doing our data collection, and it will also make the desktop application available as well. All right, so the next thing we're going to do once you get PerfView installed is actually analyze some data. Now, I'm kind of working backwards. Collecting data in PerfView is pretty boring, actually. It's by design, it's not meant to be difficult. Most of the time you're going to spend in PerfView is analyzing data that's already been collected. And I figured we would start there and take a look at some of the real data I submitted to the core CLR team to try to understand some of the issues that we'd been having with Akka.NET on top of .NET 6. So let me introduce that problem real quickly, which we're able to resolve, by the way. But let me go ahead and introduce that data real quickly and help you sort of see where PerfView might be able to help you in understanding the behavior of your own applications. So this is an issue I opened not long after .NET 6 was originally released. I think it came out maybe, I don't know, a few days before November 15th, 2021. And we have a standard benchmark that we use for measuring the performance of a single connection in Akka Remote. It's called our Remote Ping Pong benchmark. And the reason why this benchmark is so important is it's our kind of gauge as to whether or not people are going to experience a cumulative increase in performance across their Akka.NET clusters. This sort of Akka.Remote connection is kind of like the biggest performance bottleneck in our networking system. So when this speed of this system increases, it's going to make everything else faster. So one of the things that we observed is we have data that we collected on the same machine on .NET Core 3.1 and the equivalent data on .NET 6. So you'll see here, and this was taken a year ago, we're averaging about 265,000 messages per second on .NET Core 3.1. On .NET 6, the performance is closer to 300,000 messages per second. That's great. It's a big improvement. But we see this sustained drop that happens right around the 4th and 5th iterations of the benchmark. And that's been consistently reproducible for the entire life cycle of .NET 6 so far. We originally thought that this issue was related to a change that was introduced in the core CLR. Let me see if I can find this. Yeah, here we go. They changed the underlying thread pool implementation in the core CLR to move away from the original thread pool design that had been used from many different versions of .NET all the way up until .NET 5. And then in .NET 6, they switched to this new portable thread pool design. We suspected that that was the cause of the performance degradations that we saw. Other users of Akka.NET reported issues like big increases in latency between their .NET 6 version of their app and the .NET Core 3.1 version. That's keeping everything else constant. So meaning that there was no code changes, no other dependency upgrades other than moving between the runtimes. So it wasn't just us who observed this. It took quite a bit of time to try to get to the bottom of what might be happening here, but PerfView eventually helped us do it. So here's what we ultimately ended up doing. If I pull up PerfView down here, we collected several sets of numbers with some guidance from the core CLR team. They originally wanted us to take a look at garbage collection numbers and then separately look at threading numbers and also CPU sampling. So I went ahead and I collected some benchmarks, and I'm going to demonstrate how to do this in a minute. I collected some of our benchmark data running this remote ping pong benchmark, which could reproduce the problem pretty consistently. I ran this with PerfView running behind the scenes, and the first set of data we gathered was garbage collection statistics. So if I take a look at this screen here, let's see, that's CPU sampling, so that data is not going to be visible since I didn't enable it for this run. But if I take a look at the events column, you can see Windows kernel events here. We can see some built-in PerfView events. And let's see, if I take a look through here, there's some other events related to the .NET runtime, such as the garbage collector right here. Now you'll notice that there's other types of events. If you used PerfView before, let's say you were taking a look at thread pool metrics, you'll notice that there's no threading event showing up here, and that's by design. We told PerfView when we collected this data, GC was the only category that we were interested in. So that's what we got as a result. So if I go and take a look at this report that PerfView prepared for me down here, JIT Stats, let me go ahead and pull this up. This is going to give me the set of all the different processes that are running on my machine at the time I gather this PerfView data. So that's going to include a couple of things that are running behind the scenes. PerfView, ironically enough, collected data about itself. But the process we're interested in is remote ping pong. That's the one that demonstrates the problem. So I'm going to click in on here. And this will give us a nice summary of, generally speaking, how did garbage collection perform for our application. And I can see that we spent a total of 8.5 seconds roughly in garbage collection pause. And I can take a look at a breakdown here of all the different, let's say, averages by generation. So as I explained in one of our previous videos on .NET systems programming, there's 3 different generations of garbage collection. They tend to get more expensive the higher up you go. So Gen 0 should be cheap, Gen 1 should be more expensive, and Gen 2 is the most expensive. Well, we can see that on average, our GC pause time is about 3.9 milliseconds for Gen 0, 4.3 for Gen 1, and 6.4 for Gen 2. That kind of meets my expectations in terms of what I would expect. I'd expect that garbage collection would get more expensive the higher up the generation you go. And we can see that the amount of collections that we had per generation, we had about 1,850 Gen 0 collections, 263 Gen 1, 28 Gen 2. So this is kind of about what I would expect from a standard .NET application. I expect to see a lot of Gen 0, some Gen 1, not very much Gen 2. That's generally a good mix. Well, there's more detailed stats I can get into down here, such as I can take a look at GC events by time. I can see every single what's called a small allocation. This means we allocated and collected objects that are smaller than what fits into the large object heap. I can dig into that. If we had large object heap allocations, you would see those appear on here as well. And so there's a whole bunch of rich, detailed information you can dive into here. But the .NET Core 3.1 data was our control. And so if I want to try to get to the bottom of why did we have this performance regression in .NET 6, I need to take a look at our experiment, which is the actual .NET 6 data that we gathered. So I'm going to pull up another PerfView window here. Let's see, it's my .NET Core 3.1. Let's take a look at .NET 6. I'm going to open this up and expand it. And then let's take a look at our GC Stats, the same report that we were just looking at for .NET Core 3.1. And I also want to take a look at the same process, remote ping pong. Okay, we'll get a load of this. Our total GC pause time for .NET Core 3.1 was roughly 8.5 seconds. Well, it's nearly double in the .NET 6 implementation here. It's almost 16 seconds. So what could have accounted for that? The other thing we should take a look at is what's the max heap size? Like, was there any major difference in allocations happening between these two processes that could explain this? Well, the number for the max heap size for .NET Core 3.1 was, let's see, I'll scroll up here, go to remote ping pong, 219 megs versus, what was it for .NET 6 again? 215 megs. So they're within about 4 megabytes of each other. So that's probably not it. They're allocating roughly the same amount of data. But collection pause time was nearly double that in .NET 6. That smells to me like there was a regression introduced somewhere. So let's take a look at the numbers. We can see that the GC0 Gen Z garbage collection was was about twice as expensive on .NET 6 as it was on .NET Core 3.1. That is probably trouble. We can see that if I go ahead and let's do a side-by-side comparison real quick. So I'll put these numbers right next to each other. So we can see that we went from 3.9 milliseconds per collection on .NET Core 3.1 to 7.1 on .NET 6. 4.3 for Gen 1 and 6. So the overall other collection times were a lot faster, but they on .NET 6, but not Gen 0, which is the most frequent, which is why we saw such a big increase in garbage collection time. Now, this wasn't the only thing that was going on inside the application that could have potentially caused some performance problems. We also needed to take a look at the .NET thread pool as well, and also the CPU profiling data. Well, I don't have a ready-made chart to kind of demonstrate what that looks like, but We were pointed to this fix by the core CLR team after they take a look at our CPU and sampling metrics. And they mentioned to us that this bug, which was fixed in .NET 6.06, which was released in May of this year, the problem was that when threads sleep, if they know they're going to sleep for a short period of time, they'll go ahead and spin wait instead, as that's less expensive overall than putting the thread to sleep and then bringing it back, waking it up again later. Having it spin wait for a really short period of time can be more efficient. Well, the problem was that the spin wait counter was actually increasing every time it was called. And that's why we would see this sort of regular pattern of the thread pool slowing down around the 4th or 5th iteration of our benchmark, was because the spin wait value got significantly higher. And the reason why this affected Gen 0 garbage collection so much more was because the Gen 0 garbage collection happens on the threads that were performing the allocation in .NET, and there was a lot more of them. As a result, that cumulatively drove up the spin wait factor for all those threads and caused those pause times to increase. So it was a bit of a misnomer. It wasn't that the garbage collection system was actually underperforming in .NET 6. It was that a bug in the threading system itself was affecting how the garbage collector ran. So we were able to get to the bottom of that using this PerfView data. So the next thing we should take a look at is how to actually collect some of this PerfView data ourselves. So the next thing we're going to do is collect some performance data on one of our other benchmarks in Akka.NET using PerfView, just to kind of show you the ropes on how that's all done. This is a little Notion page I wrote for our team on how to actually run PerfView. And there's a whole bunch of different command line options you can use. We're going to use this one right here, which is a headless version of PerfView, so meaning that there's no GUI at all. And we're basically going to go ahead and gather all of our threading and sort of JIT symbols and all that. This will help us kind of do some CPU profiling. Whereas you can see down here, this command is what we use to analyze that previous data set that we were taking a look at. That's all garbage collection values only. So what I'm going to do is I'm going to paste this command into my terminal here. I'm not going to explain what all this stuff does, but long story short, I'm using a circular buffer to make sure that the amount of memory that PerfView uses to store data doesn't exceed 4 gigs. So I've got that set up in my administrator prompt here. And in my other prompt, I'm going to go ahead and key up my actual benchmark. So this should run my .NET 7 version of our in-memory ping pong benchmark without profile guided optimization turned on. And we want to compare PGO versus non-PGO. So we're going to have to gather 2 sets of benchmarks. So it looks like data collection has started. All right, that's great. And now I just need to launch my process. And let's see. I can go ahead and see that we're starting to collect some real data now. So you can see that appearing in this little program window behind the scenes. Benchmark is actually properly starting now. And we can start to see some records begin to come in. This is perfect. So I won't go ahead and bore you with running the entire benchmark here. So I'm going to go ahead and pause real quick, and we'll resume when it's time to turn off data collection. All right, so my benchmark has completed now, and I'm going to go over to the PerfView window, and I'm going to press S to stop collection. And this is going to stop collecting any more event tracing for Windows data. And it's going to have to take all the different files that we produced and collate them together into a zip file that I can open and analyze in PerfView later. So I'm going to go ahead and turn that off, and we'll pick back up once the data from this sample is available and the one I'm going to do with profile guided optimization turned on. So we can try and compare some of the 2 values. So apparently my web camera stopped working when I unpaused it last time around. Sorry about that. We have both of our data sets now. One data set where we are analyzing our in-memory ping pong benchmark without profile guided optimization, and another one with profile guided optimization turned on. And if I pull up the command line, you can see that the max values, so we're approaching 96 million messages a second here, are quite a bit higher than the 61 million messages per second we were doing without profile guided optimization. So we want to take a look at the PerfView data and see if there's anything we can see in there that might explain the difference in performance between these 2 different configurations of the same application. So what I'm going to do is open up both of these zip files in their separate instances of PerfView. So I go to PerfView, and I'm going to copy my little directory here, paste it into the PerfView window. And I'll see both of these zip files available. And I'll go ahead and load my control data here, which doesn't have PGO enabled. And I'm going to grab a second PerfView instance. Let's do that. And we'll go ahead and start loading the other one too. So I'll go ahead and grab our PGO data. Okay, now this can take a moment. So both of these files are roughly 130 megs, 110 megs. So these can take a little while to open up and expand. However, all of our data is available now for our test case. So let's take a look at our CPU stacks. If I pull this open, and let's take a look at ping pong. That's what we want to see. Okay, so this is ping pong, and it's going to analyze the most expensive parts of our application. One of the things that we can see, and this makes sense to me, is that the function that has the highest number of sort of inclusive samples inside our benchmark is going to be the mailbox.run. This makes sense. Every single time an actor needs to process a group of messages, this function is going to be behind that. So that's going to be a big one. And if I take a look at our flame graph, you can kind of see these peaks and valleys. This kind of matches when the actors are being scheduled to run, most likely. We can see that we start with a mailbox.run, and that gets called after a work queue dispatch. And then we can see the actor receive methods being called inside of here, and that goes down to the actor cell.send message. So this is when we're processing a message. This is when we're sending a reply back. And then what's this? This is when the message is being enqueued into the envelope of the other actors. So these flame graphs actually do a pretty good job of helping us understand what is happening during all these iterations inside the benchmark so far. Let's go ahead and take a look at our data with PGO enabled. Let's see if the CPU stacks help us at all here. Let's take a look at that. Okay. Still dominated by mailbox.run. That makes sense. That's what we would expect. Let's take a look at the flame graph. Let's see, just about the same as what we had before. Now, this is where things get a little interesting. Let's see if I can zoom in on this here. Okay, this is an example of, let's see, is this the receive actor doing that? It might be. Let's take a look. Client actor base.receive, client actor base.display. Client receive actor. Okay, that's a receive actor doing that. So that's not super interesting. I thought for a moment we could see examples of the JIT basically kind of changing things up. That's what profile guided optimization does, is allows the just-in-time compiler to make some bets and try them out. And if the performance improves, it keeps them. But so far, all these Lambda methods we're looking at, these are all part of the receive actor. That's kind of expected behavior in the system. So the flame graphs, while helpful in understanding the performance of the application here, aren't really telling the story about what's the difference between PGO and non-PGO behavior. So the next thing we might want to take a look at is go into advanced and see if we can see any JIT stats in here. Let's see, this is the non-PGO, this is the non-PGO version, okay? Let's see if this opens up. All right, JIT stats here. And is there a way I can break this down by process? That's JIT stats for PerfView. That's not super interesting. This is probably our application. Let's scroll up to the table of contents real quick. Okay, process ping pong. Okay, total number of compilations. Bear in mind, this is without profile guided optimization turned on. We did 4,913 total compilations, roughly half of which occurred in the foreground. Actually, 45% occurred in the foreground, 55% occurred in the background using tiered compilation. And we could probably break into the low-level stats on that a little bit more if we wanted to. Okay, well, that's one set of data. Let's take a look at the PGO data. Here we go. Go into advanced. Let's take a look at JIT stats here. And let's look at ping pong. And if we take a look at this, the total number of compilations is roughly the same. However, let's take a look at these two values. So we spent, let's see, total amount of processor time spent JITting was actually slightly higher in the PGO example. That's something that we would expect to see. But let's see, individual JIT events. Let's take a look at this. And let's take a look at this as well. We're going to go ahead and compare these side by side here. So let me put them up into separate windows real quick. And yeah, we have to export to Excel, I guess, to view all these. That makes sense. So far, looks pretty consistent with each other here. We can see some dynamic classes being created. This is probably as a result of some of the delegate work that we do. And then if we keep digging into some of this here, we might be able to get some answers on how PGO outperformed regular .NET 7. The last thing we can try taking a look at is some of the events themselves. Let's take a look at this. Let's see. We would want to take a look at the JIT events inside the core CLR. CLR walk, thread create, GC stop, loader, dynamic module unload. Okay, tiered compilation. Settings, take a look at this. Quick JIT, JIT for loops. Here we go, we can see some tiered PGO inside here. Okay, and if we see background JIT start, pending method count. Well, we can see some signs of tiered PGO running in the background there. Let's take a look at our normal .NET 7 values. And I'll take a look at the events here as well. This is without PGO being enabled. And let's take a look at our JIT events here. Tiered compilation settings. And you'll notice there's no PGO events enabled here. So we can definitely see that the just-in-time compiler is emitting separate events. However, in order for us to dive into it and understand why our application performed better with PGO versus without it, that'll probably take a lot more introspection and a lot more digging through these numbers. But the purpose of today's video is just to show you how easy it is to use PerfView to collect this data and how shareable it is. I can put this data into a zip file on Dropbox and send that to the core CLR team. And in fact, that's how we diagnosed that previous issue I was just showing you. So the next thing I'm going to dive into is some more resources you can look at for trying to learn more about PerfView and trying to go ahead and try it out yourselves. Now, like I mentioned earlier, there's not a huge amount of resources available online for PerfView because it's a somewhat esoteric tool that's largely used internally by the .NET teams themselves. However, it's all available open source, and you can go to the Microsoft/PerfView repo to get access to the latest. And on top of that, these original Channel 9 tutorial videos that the creator of PerfView, Lance Morrison, put together, those are still available. Even though those videos are a little old, they're all about 10 years old now, they're still good. I remember using these to teach myself how to use PerfView and ETW to track down a really nasty bug in early versions of Akka.Remote that we were writing back in like 2013, or maybe it was early 2014. But either way, this is still helpful. Lastly, there's the PerfView User's Guide, which will include links to all these in the footnotes for this particular YouTube video, but this includes all the different command line options. So if you have really specific metrics you want to look at for being able to profile your application, this will help you do it. So I hope you found this video helpful. Please go ahead and give us a like and subscribe. And if you have any questions about PerfView or about this video, please go ahead and leave them in the comments. Thank you very much.